All right, so we're going to move into the final section of this course, the predicate calculus, where we learn to do proofs in predicate logic. In this lecture, we're going to focus on one of our new rules, which is the rule of universal elimination. So the predicate logic is an extension of propositional logic, as you know, and the predicate calculus is just an extension of the propositional calculus. So we'll be using all of the rules that we developed in the propositional calculus and just adding a few more. So there's four actually new basic rules for using quantifiers. These first four rules are inference rules. They're not equivalences. And you'll remember this means that when you use them, you always have to be working on the main operator, which in this case is going to be a quantifier whose scope is the entire formula. So the two rules that concern the universal quantifier are universal elimination and universal introduction. And the two rules that concern the existential quantifier are existential introduction and existential elimination. And that's the order that we're going to introduce them in. So in this lecture, as I said, we're going to focus on the first one, which is universal elimination. Okay, so universal elimination is basically just a rule that allows us to pull the quantifier off of and substitute a name for every occurrence of the variable that the quantifier was binding. It's what we call an unrestricted rule, which means that you can do it anytime you want to any name you want, as long as the universal quantifier is the main operator in the formula. And of course, this makes intuitive sense when you think about that. If you think about a universally quantified proposition like everyone is happy, which we would characterize as for all x, hx, well, that means everyone is happy. So surely you should be able to infer from the fact that everyone is happy that Alvin is happy, or Bernice is happy, or Charlie is happy, or Denise is happy, etc. Not just or, but and. You can infer anyone you like. So let's look at a simple example of how universal elimination works in a proof. So let's try to prove this. We have for all x, fx as an assumption, and for all x, if fx, then gx as an assumption. And we're supposed to prove GA. So if you just look at this for a second, you can see that there's an interesting relationship here. It looks like there's an interesting relationship here of a conditional elimination nature, right? I mean, imagine that you had FA, and then imagine that you had if FA then GA, then you could apply conditional elimination to get GA. So what you do is you choose your name judiciously. I mean, we see that we want GA up here, so it would be kind of ridiculous to do just anything like to eliminate to B or C or D. We want A, so we get A. So we have FA from 1 in universal elimination. For all x, f of x goes to FA. We pull the universal quantifier off and stick the name A in for x. And similarly with line 2, we pull the quantifier off. And of course, it would be, we could have written if FB then GB, but that would be pointless because what we're trying to derive is GA. So we go to the very same name, and that's okay because you're allowed to go to any name whatsoever. As we said, that's an unrestricted rule in this sense. Now later on, we'll find that other rules are not unrestricted. So this is just a feature of this particular rule. And since we have FA and FA then GA, we now have GA by the familiar rule of conditional elimination, and that's what we wanted, so this proof is over. All right, so just to emphasize what we've already said here, remember that we're able to choose, with universal elimination, we're able to choose any constant we want, and normally we're going to be doing that intelligently by going for some constant that we need. And secondly, note that when we do substitute a constant, we do it for every occurrence of the variable. So, for example, on line 4, it would not have been open to us to leave an x there. We could not have written, for example, if fa then gx. And there's two reasons for that. One is that, well, the rule just doesn't permit it. But the other, there was a reason why the rule won't permit it, because this is not a well-formed formula. X is now occurring without a quantifier, and it's unbound, and that's not a permissible formulation in predicate logic. Okay, now here's another example, and it involves multiple applications of universal elimination. Actually, the previous one had multiple applications too, but this is even more. Again, fairly straightforward. So we have two assumptions for all x and for all y. If fxy, then fyx. You can see the order of the variable is being flipped here, which is an interesting thing to note. And then for all x, fax. Now, importantly, don't think that the x's in assumption 1 and assumption 2 have anything to do with each other. We might be able to make them have something to do with each other by judicious application of the rules, but these are occurring in different formulas. And remember, variables don't have any inherent meaning to them. So we could have used z, but we don't have to in the second formula. Okay, so what we want to prove is FDA. We want to derive this formula, FDA. And the question is, how can we do that? And it's a little bit tricky, but if you stop the video and look at these relationships, I think you'll probably be able to figure it out. So if we were to do a universal elimination on 1, notice that we have to start by operating on this quantifier. We can't do them both at the same time. And so what we're going to do is remove this quantifier and put some constant in for this quantifier, so for this variable x, right? Now, and also we'll have to go for this variable x. So you just have to ask yourself, which one should you do? Now, there's two possibilities here, right? There's A, and then there's also D. The question is, which one would really make the most sense here? Well, we know that we have this for all x, fax, right? And we have x here, so it seems like it would make sense to match this A with this A, especially since this is going to ultimately be flipped by this conditional. So again, sometimes you just will be wrong about this, but let's just go ahead and try this. So let's go ahead and go to for all y, fay, then fya. Okay, so what we've done is that we've applied the rule of universal elimination to 1. We've removed the first quantifier. Second one is still there, and we've substituted an A for both occurrences of x. Okay, now what if we just did this again? Now again, we could just go to FAA if we wanted to, or we could go to FAB or anything, but clearly D is what we're looking here for, so why don't we try that? Now we've removed the second quantifier, and we've got if FAD, then FDA by 3 in universal elimination. Okay, so two successive applications of universal elimination. Well, now you'll notice that we have FDA coming out the end here, which is what we want. So if we think, say, in terms of conditional elimination, it would be really nice if we had FAD. Is there any way to get FAD? Well, look at 2. For all x, FAX. So apply universal elimination again, this time to 2, and you've got FAD. So you can see the process here. Essentially what we're doing is we are taking these quantified expressions, in this case all these universally quantified expressions, and we're sticking constants in. And the reason we're sticking constants in is because once we have these all have all of the universal, in this case universal, but all the quantifiers removed, then we're left with our familiar rules of propositional logic. So that's the basic approach to doing predicate logic proofs, is to apply the rules for the quantifiers so that we can sort of render them into propositional logic proofs. So now, of course, you know how to get FDA. That's just by 4-5 conditional elimination. Make sense? Okay, so again, just a reminder, remember that we were only ever able to operate on the quantifier furthest to the left, which in this case is the one whose scope is the entire formula. Don't let me give you the wrong idea. Just because a formula is on the very left, just because a quantifier is on the very left doesn't mean it's the main operator. So for example, if I have for all x, fx, then say there exists a y, gy, well, what's the main operator there? The universal quantifier is on the left, but it's not the main operator. This is the main operator, okay? So in this case, you would not be able to do anything to for all x, fx, because it's not the main operator. If it had been written differently, if it had been written like this, for all x, if fx, then there exists a y, gy, then you could operate on this, okay? But you would get a very different formula as a result. And that actually leads us into ways of misusing universal elimination. So here is a way to do it incorrectly. So again, we're being asked to prove this. For all x, fx, or for all y, gy, yields fa or gb. So we're just given one assumption. Now suppose we do this. 2 applications of universal elimination. Can you tell me what we've done wrong? Okay, so I hope you got that. The answer is simply that we've failed to operate on the main operator, just as we were discussing before. In this case, the disjunction, over here, the disjunction is the main operator, so we're just not free to operate on any of these universal quantifiers at this point. Now you might ask yourself, okay, is there any way to do this problem then? And the answer is yeah, you can do this, but you're going to need to use OR elimination. So let's go ahead and do that. How are we actually going to do this proof? Well, what we're going to do is use conditional introduction and hypothesize for all x, fx. And then from for all x, fx, we're going to derive fa or gb. And that's actually not difficult because we can get fa by 2 in universal elimination and just add in gb by 3 in OR introduction. So then remembering how to do conditional introduction, right? And if you don't remember, you got to review this. We now have if this, then this, right? Take away the indent, drop the line. So now we have if for all x, f of x, then fa or gb. Repeat the process with for all y, gy, and it looks exactly the same, right? So now we have 1, 5, and 9, and our good old rule of OR elimination allows us to conclude FA or GB. Why? Because we've shown if for all x, fx, then FA or GB, and if for all y, gy, then FA or GB. So we've demonstrated that FA or GB follows from both of these independently, which is what the rule of OR elimination does. Okay, now one other thing that it's important to remember, I've actually reminded you of this toward the end of the one of the previous lectures, that it's important to understand that just the existence of a particular quantifier in a proof doesn't mean that you have to use a particular quantifier rule. Sometimes you can just use the propositional logic rules on quantified statements. So take a look at, this is just a very simple one, but it's all we need to remind ourselves. Take a look at this. This looks kind of thorny initially. We have two assumptions, for all x and for all y, if fxy, if for all x and for all y, fxy, then there exists a z, g, z. We're also given it's not the case that there exists a z, g, z, and we're being asked to show that it's not the case that for all x and for all y, fxy. Now, if you're just starting out, you're going to say, okay, let's get busy here operating on these quantifiers, but just look at it for a second. You'll see you don't have to. This is the negation of this, right? Exists as z, g, z, pop a negation on the end. We have the negation of that. And so if you just apply modus tollens to that, you actually get the negation of this formula, which is all they were asking for. So something that looks very difficult actually turns out to be dead easy if you make sure that you explore the ways that you can just use propositional logic on predicate logic formulas. All right, so let's just take a look at a formal statement of universal elimination using the meta language. So everything we've just learned here amounts to this very compact statement. For any universally quantified formula for all Vp, we may infer any formula that results from removing for all V, removing this, and inserting a single name letter, A. Now remember, A is just any name at all. This is a variable in the meta language, so just any name at all, for every occurrence of V in P. Now, what does that mean? Well, just first of all, note that P here is meant to stand for any formula at all that contains a variable or multiple occurrences of a variable. Okay, so this says for all Vp, we can remove this, okay, completely, and then just for every occurrence of V that was in P, to the extent that V was in P, we substitute a particular letter, the same letter, for every occurrence of that letter in P. And that's what we've been saying. That's what we've been doing. So, you know, in the simplest case, if you have, say, for all x, fx, that means you can write fa, or you can write fb, or you can write fc, all justified by universal elimination. And in a more complicated case, say you have for all x, there exists a y such that if gxy, then fyx. What this means is that you could, if you would like, write there exists a y such that, remember substituting for x, g, a, y, then, and remember you have to substitute for every occurrence, so fya. And similarly, if you wanted to say there exists a y, g, b, y, then fyb, etc. Okay, so the important thing here again is to realize the only reason you can do this is in both cases these are the main operators. If this existential had been a universal, you could not operate on this until you had removed the first operator. Okay, now let's finish by just doing a little reminder about the negation and contradiction. So remember that to negate a formula is simply to attach a negation to the outside of the formula, right? So if you have a formula, call it A, right? Then if you want to negate, if you want to say negate A, all you do is you negate it like that. Right? That's all there is to it. Now, I think this probably sounds pretty obvious, but let's just go ahead and apply this to predicate logic. So if you have a formula like for all x, fx, how would you negate that formula? Well, the answer is you put a negation on it, right? So it's not the case that for all x, fx. And importantly, this is not the negation of this formula, right? The negation, you can't insert a negation here and get the negation of this formula. So this is something completely different than this. This says, let's let FB say funny. This says it's not the case that everything is funny, so something's not funny. But this says nothing is funny. For all x, nothing is funny. Very, very different statements, as you know from studying predicate logic. Now, why am I reminding you of something so seemingly obvious? Well, let's think about it in terms of contradiction. This is a contradiction, right? How do you know that? Well, because you've got a formula, A, and its negation. There's just a negation on the outside of that formula. This, however, is not a contradiction, right? Why? Because we don't have a formula and the negation of that formula. Now, again, this feels obvious, I'm sure, because we're presenting it in this way, but it's really easy, very easy to forget this, especially when you're looking for a contradiction. You find yourself saying, well, is this a contradiction? Is that a contradiction? Well, that's one of the easiest questions to answer. You just don't always necessarily like the answer. The answer is, well, can you just break off the negation from one of them and produce the other formula, right? And that's the only way you have a contradiction. If there's a negation on the outside of one of the formulas and breaking it off produces the other formula. So you've always got to submit yourself to that if you're going to assert that two formulas are contradictory. Okay, so let's go ahead and finish with just a one round of study questions where we'll develop just a single proof. And what I want you to do is just state whether the last step, the highlighted step of the proof, is done correctly. Either that, or if it's not finished, provide the missing justification or formula that would make it a correct step. Okay?